In this session, we're going to be talking about cross-origin resource sharing. We're going to try to cover a lot of ground, looking at all of the elements of CORS that you might need to consider from a security testing perspective, as well as from a developer perspective. So let's get into it. Here is my own personal definition for cross-origin resource sharing. This is another topic where I find that a lot of the definitions that you find are not quite accurate or complete. So in this case, I'm calling it a mechanism for servers to relax default browser protections applied to cross-origin requests, permitting additional request types and data reading capabilities. So it's a browser protection mechanism that exists, roughly governed by same origin policy, and CORS is what allows servers to be able to relax it, right? So the directives to relax the protections come from servers that we're communicating with, but the browser both applies the protections, and when it's given the directives through CORS rules or CORS permissions, we could think of them as, it's able to relax those protections when making cross-origin requests, hence the name cross-origin resource sharing. There are resources that we want to share cross-origin. Now, crucially, in this definition as well, CORS can let us make additional request types that we normally cannot make. And it also primarily allows us to read data. Now, a lot of people reduce CORS to this data reading capability, but the ability to construct additional requests is also very, very important from a security testing point of view. So CORS presently, it used to have its own specification. Now it's captured within the fetch API, and this is a quoted definition from it: to allow sharing responses cross-origin and allow for more versatile fetches than possible with HTML's form element, the CORS protocol exists. It is layered on top of HTTP and allows responses to declare they can be shared with other origins. And if you want to read the full specification, which, hey, might be interesting to you, it is quite long, but there's the fetch spec linked. And of course, because this is so intertwined with the fetch API that is available in browsers, it really is worth talking about fetch, a little bit of background, how it's used before we get deep into CORS. So the fetch API is a mechanism to send requests and obtain resources. It is the modern JavaScript API for sending HTTP requests. It replaces XML HTTP request, which you'll also see referred to as XHR, though that mechanism is still very, very common across the web. It's still supported, of course, by browsers. The API is implemented and consumed by browsers. I say that primarily because I do think that there are other JavaScript engines that are not based in browsers that support the fetch API. I don't know the full set of those. As far as the security rules around fetch, they are implemented and enforced by browsers. Fetch, as far as the JavaScript specific considerations, is promise-based, and it's asynchronous. And that has an important role in fulfilling what traditionally has been called AJAX, which is a term for asynchronous JavaScript plus XML. That notion has kind of evolved a little bit. It's not, generally when people say AJAX, they're not necessarily exclusively referring to XML. And I now just think less and less people say AJAX. It was more of a term at the onset of what you might call Web 2.0. So whereas Web 1.0 was you go to the internet and you navigate to a page, and that page just loads all of its resources at one time. Well, now we have the notion of asynchronous JavaScript, where JavaScript logic runs in the page, and as you're consuming functionality on that page, in some cases to get more data and to update that page, you don't need to navigate to a different page. JavaScript can make calls just to specific components, retrieve specific pieces of data, and update that page live dynamically. So those calls are made asynchronously. And the fetch API, of course, is configurable to send a wide range of request types, and we are going to look at those. And I do have a little note at the bottom. What we're not going to look at is XML HTTP request. I don't think doing a deep dive into it would add much of a benefit from a security testing perspective. But it exists, it is in use, and you will see it nevertheless. So here is the fetch API in use, and we're just going to make a very simple same origin request. So I just did this. I just navigated to in my browser to Google, and I opened up the developer tools, and I went to the console, and I pasted this JavaScript, which is not grabbing a different origin. It's using my current href, that it's just grabbing from that document, and I'm sending a request, and I'm reading the response, or yes, I'm ultimately posting the length of it, right? So being able to get the length of a response requires the ability to read that response. And because we're submitting this request on the same origin, we are permitted to do so. We're not blocked by any of the rules of same origin policy. We are meeting same origin policy. It's a same origin request. We're going from a Google page to the same Google page. I mean, it doesn't really matter as long as it's on the same origin. We could grab other resources belonging to Google. We don't need CORS in order to be able to retrieve and read this data. And if you capture that request in your browser, this is what it will look like, or sorry, not in your browser. If you capture it in Burp Suite or another intercepting proxy, this is what that HTTP request will look like. We're going to explore some of the elements. By elements, I mean request headers. When we dive a little bit deeper into the variations in requests that can occur as a result of CORS and no CORS. But this is what it looks like. For anyone who's read raw HTTP, it should look fairly straightforward. One thing that is notably absent from the same origin request is the origin header. There's no origin header. Isn't that interesting? Now, here's what happens when we try to make a cross-origin request. And we're trying to make that cross-origin request to a remote system that doesn't support CORS. So it's not granting us any permissions to read the data cross-origin. This is the same situation where I'm in my browser, I've navigated to google.com, and now I'm making a cross-origin request to example.com, and I'm trying to do the same thing. I'm trying to just read the length of the data. And you'll see what happens in the browser in the console image at the bottom. We get an error, and the error in this case is nice and clear. It says cross-origin request blocked. The same origin policy disallows reading the remote resource at example.com. So we have a situation where CORS is preventing us not CORS, same origin policy really is preventing us from reading this data. And in order to do that, we would need CORS, which is absent. So it says, the reason we can't read this is really because of CORS in the browser error. Ultimately, it's really because of same origin policy, but you could also think of it as, if the expectation was there was a CORS policy to allow us to read it, yeah, that is missing from that perspective. And here's what that looks like in Burp as a raw HTTP request. There are two differences here, of course. The main one is that we are reaching out to different hosts. So the host header changes, and the ultimate destination of this request is different as well. We're no longer sending this to a Google server. We're sending it to the example.com server. But you'll also notice the introduction of an additional HTTP header on line 8, and that is the origin header that is now specifying the origin from which we are making the request. So our browser is sending contextual information about where our request is coming from that's going to the remote server. And it also includes other headers for this purpose, which we'll talk about momentarily. We won't talk about the refer header in the session, but we will talk about those odd-looking sec fetch headers known as fetch metadata. But first, just a few more items around the fetch API. It's actually quite a complex API. The specification is not a short one. It's not necessarily a light read. There are many ways in which we can configure fetch requests, and this screenshot here is really just showing, or this code snippet is really just showing some of the ways in which you can configure it. We are not going to look at all of these properties that you can set on it. It is also important to note that, but again, we're not going to dive deep into this. There are ways in which you can handle errors as well relating to the success of the requests. And in some cases, we'll look at in a future session how this could potentially be abused for types of cross-site leak attacks. What are the restrictions without CORS beyond being able to read data cross-origin? There are also certain types of requests that we cannot make. So when I make this request and I specify explicitly, I would like this to be a no CORS request, so as not to require CORS, we cannot use the delete method. The delete method means that our request is no longer simple, and therefore the browser does not let us make that. There is no world in which we can make a delete request without CORS, or without CORS, I'll say. So If we do make a delete, or if we attempt to make a delete request with CORS, then that initiates the process where the browser effectively seeks permission in order to make that request. And in this case, I'm sending another cross-origin request. Remember, again, from the context of google.com, as you can see in my origin header on line 9 in the HTTP request taken from burp, we have, again, www.google.com plus the HTTPS protocol. That in totality is specifying our origin. And the, well, a couple things worth noting in the response. First of all, the options method just is not allowed by that target, so there is no way in which this was going to work. But it also doesn't return the appropriate headers that give us permission to send a delete request. So this options request that you're seeing here, we didn't try to make an options request. We didn't necessarily intend to make an options request. It is a precursor for certain types of CORS requests to first get permission from the remote server in order to be able to send the requests that you want. And it is called the pre-flight, and we will look at that in more detail later on. But first, as I mentioned, we're going to talk briefly about fetch metadata, and this will come up more times in more sessions in the future, particularly when we're talking about cross-site attacks and things like cross-site request forgery, or what you might call browser-based request forgery, perhaps a more appropriate name. Nevertheless, fetch metadata is metadata that is now sent by modern browsers in the form of HTTP headers. So this is additional contextual information about the nature of the request you're making and the context of that request in comparison, in particular, to the target application or origin that you're sending that request to. It is not defined in the fetch specification, I don't think. I can't remember what all the references to it are, but there is a separate specification that you can read about in that first link. And as I mentioned, the browser enriches HTTP requests with this contextual information. It was kind of interesting in being a security tester for so long. This is one of those features that when I first started didn't exist, and then one day you start seeing all the browser requests that include this data. It feels a lot messier than the web used to be, but it is really interesting and oftentimes useful information to have. I won't tell you all the ways in which it'll be useful. I might mention a couple of tips and tricks, but for the most part, we're introducing this topic at this point because I think it makes sense in the context of talking about fetch and talking about CORS, but it applies in a lot of situations beyond this session, which I won't touch on all of those. So this includes 4 distinct headers: secfetch site, which indicates the relationship between the source and the destination for that request that we're making; secfetch mode, which indicates the mode of a request; secfetch user, which is set to $1 when the request is triggered by user activation, formerly known as a user gesture, so something like clicking, something like interacting with the application in some way, activating that behavior within the client-side web application. And as far as I can tell, this is implemented, this particular header is implemented in all browsers, or all modern browsers, I should say, except Safari, as of now, January 2026. I don't know whether it's coming to Safari. It's something that, personally, I haven't paid that much attention to. It's something that web applications could potentially use when they're receiving it. But I think, because Safari makes up such a large market share, applications that begin to rely on it would probably exclude or make things difficult for a bit of the user base. Finally, we have secfetch dest or destination, which is the context of the request in the originating app. Dest, which I'm pretty sure stands for destination, can be a little bit, I think, confusing in that it's not like the destination of where we're sending our request. It's about, we're going to obtain a resource from somewhere, and that resource has some destination within our client-side application, and that's what we're talking about here. So that component in our application that is making that request, ultimately that data is going to go back to that component, and that's the final destination, especially in the context of CORS, which is mostly about the ability to read and interact with data across origin. So looking a little bit more in depth at some of these headers, secfetch site can only have one of these values. And one thing that I point out here is what the implications are from some of these settings that can sometimes be a little bit confusing. So there's no value, for example, for a cross origin request. And the reason being is there doesn't necessarily need to be. You can infer from the value when a request is cross-origin. So anything that is cross-site is necessarily cross-origin. Anything that is same site, anything that is same site in theory isn't necessarily cross origin. But because there's a same origin value, the fact that the application is not sending same origin tells you that you can know that the request, if it says same site, is same site but not same origin. And the final option is none, which applies in certain situations, like you copy a URL directly into your browser, you navigate to an application. Sec fetch mode has a number of modes, not all of which are relevant to us right at this moment. Of course, the two that are important are the CORS and no CORS, which indicates whether the request is CORS mode or no CORS mode. And most applications don't really use this for anything, as far as I can tell. I maybe mentioned that these headers were relatively new, and we might see more features built around validation of sec fetch metadata, or fetch metadata, sec fetch headers, but we don't see a lot of that just yet. But from a security testing point of view, if you're looking through a lot of traffic in an application and want to better understand the context of certain requests, the mode can actually be very helpful for that purpose. And, so can sec fetch site, really all of them, depending on what you're looking for. So one thing I will make a little aside recommendation for as far as security testing, efficiency in workflows, is that these can make good filter targets if you're trying to look for certain types of traffic that your application is sending. So assume you're working from a modern browser, which I assume everyone is now, that enriches HTTP requests with this data. If you're looking for specific types of requests, using these headers in combination can really help you narrow down certain types of requests that the application makes. Finally, we're going to look at sec fetch dest. And as you can see here, this is referring to ultimately a component in your client-side application. So iframe is a valid value, for example. So if you have a request that's originating from an HTML iframe that is embedded in a page, it's going to include iframe. And there are many, many more values that this can represent that I haven't included here. And we don't really need to go into detail for the purposes of this presentation, so I'll stop there. So one of the things that I see that's very pervasive, and again, or did I mention that yet? If I haven't, I'll mention it now. You can search CORS and Reddit and see developers losing their minds over CORS errors and issues. And I do think that's probably one of the big origins for why we see insecure CORS configurations, is that it is a little bit confusing of a topic, and what makes it harder is that a lot of the resources are not fully accurate and present CORS in very, very different ways. And I hope that the way that I presented today is easy to grasp and make sense. Love to hear some feedback if anyone's willing to offer it. But this was just one example that I picked because I think it was the top result from a Google search. Of course, Auth0 is a very prominent organization that has probably a significant influence on the security industry broadly. And I just wanted to focus on some of the wording here. They say JavaScript can only make calls to URLs that live on the same origin as the location where the script is running. And that's not true. That's only true if we assume that call means the capability to actually read the data in the result, which I don't think is really apparent from that terminology. Goes on to say, for example, if a JavaScript app wishes to make an AJAX call to an API running on a different domain, it would be blocked from doing so thanks to same origin policy. Again, using that terminology, call to an API running, like, do we mean it must have necessarily the capability to read it? I don't think that's clear from the wording. That often is a very confusing issue. It's also very common to see people refer to CORS as a mechanism that only concerns the capability to read data, which is not entirely true either. As we'll see, it also gives us the capability to initiate requests that we couldn't normally initiate. And I see the same kind of issues propagate in language models. So this is ChatGPT, just as an example. And these aren't even, I think, the best examples, because I've been using it to review some of the content for these, and to see what types of answers it gives, and how that compares to specifications, and how it compares to forum posts and things like MDN. And there are a lot of conflicts that occur all the time. And so just looking at the left image, CORS does not prevent requests from being sent. That might be something that is technically true, in the sense that you could maybe consider it same origin policy that is what is preventing things from being sent, because CORS ultimately is just a system to allow more things. But practically speaking, CORS does allow us, with a permissive configuration, to send requests that we couldn't normally send. So I think that that's misleading or confusing at best. As one example, in looking on the right-hand side, when is CORS triggered? CORS applies when all are true. JavaScript initiates the request targets a different origin, script attempts to read the response. And that's not true either. Not all of those are necessary requirements for when CORS will apply. And hopefully that'll be a little bit more clear after the end of the session. So now let's introduce CORS in a little bit more detail. So CORS can only relax same origin policy. You can't actually return CORS headers that apply a more strict configuration. CORS basically is just relaxing security, right? So if you want to avoid security risks that are posed by CORS, simply do not return any of the headers from your server that are related to CORS, and then that's it. That's real easy, right? Now, if your application needs to support cross-origin reading capabilities, then you do need to support CORS, and there are secure ways to do that depending on what you're doing. So CORS also permits cross-origin access to read potentially sensitive data. Now, I say I add this as a second point because oftentimes when we're thinking about embedding resources and accessing resources from other applications, a lot of the time that we do that with the composable web is just for the purpose of taking static resources and placing them accessible within our application. But CORS, under certain circumstances, gives us the capability for to make authorized requests on behalf of users to some application that they have an existing trust relationship with, and then if the CORS policy is permissive enough, we can read that data. So there's potentially quite sensitive things that are make up users' data with sensitive applications that we can read using a permissive CORS policy. Of course, crucially, it is opt-in by the server. So again, if you completely ignore CORS, assuming your application framework is not returning a permissive policy by default, but if you're not using CORS, you're not opening up this potential security gap. It is only opt-in by including the appropriate access control allow headers, which we will look at in further slides. It's enforced by the browser largely through the fetch API, as discussed. And again, I mention it again and again, often considered to only permit cross-origin reads, but it can also permit additional HTTP requests to be sent by the browser, types of requests that we couldn't normally send. And in general, it's considered a modern replacement for old hacks like JSON-P, which existed because CORS didn't exist. Is CORS the best solution, best replacement for JSON-P? Maybe, but certainly we've seen a lot of improper and insecure uses in practice. So here is a very simple example. Whereas before, from Google, we interacted with a remote application that didn't support CORS. It didn't return CORS headers. In this case, this is an application that is designed to support testing of, I guess, JSON interactions. And that's one important thing to note, is that by default, with requests in your browser, without CORS, you can't send a request with well-formed JSON to some other application cross-origin. And so what we're doing here is sending some JSON data, and this is a CORS request. So we need permission from the remote server, and ultimately we do get that. Oh, actually, no, sorry. In this request, we're not sending JSON data yet, but we are reading data from the server. I think in a subsequent example, we look at sending JSON data. I had to just read it quickly there. But the important thing here is that we're making a request cross-origin, And down at the bottom, we're reading the data that we get back from that application. Now, this isn't interesting or sensitive. It's a test site, but it shows us that using CORS, we can actually read data in our client application from a remote application that's hosted on a different origin. And what does that look like as far as the HTTP? If we're looking at this in Burp, well, as you can see, we have the origin header that is included in our HTTP request. And in the HTTP response, there are two access control allow headers. The one we're just going to focus on right now is the access control allow origin, which in order for us to be able to read the data, has to exactly match the origin that we are sending our request from. And as you can see, it does. Now, in this case, and this is also worth pointing out, the application that we're interacting with was not designed specifically to interact only with Google. The behavior that's happening here is we have sent this origin value, and the application has logic that takes that value and builds it into the access control allow origin header. And we'll look at that more a little bit further in the slides. Importantly, we would call this a reflected origin header. So we send it a value, it sends that value back to us. And as an aside, this tends to be the most insecure configuration that we see here, and we'll go deeper into that in a bit. Now we're on the example we're actually sending JSON. Sorry for the confusion earlier. You can see that we're creating a fetch request specifying the method as post now. In this case, we have now a body where we're adding a JSON object, and we want to specify a JSON content type, and so that's what we're doing with the headers. And doing all of this requires CORS. And with this specific configuration, we are going to send we're going to have to send a pre-flight request in order to confirm with the application, hey, can we actually send data structured in this way in our HTTP request? And so as you can see in my Burp history down at the bottom, the application first sends an options request, request number 264, and then only after getting permission does it send request 265, which is a request that includes a JSON string and a JSON content type within that HTTP request. And looking at that in Burp, this is what we see. This is what the browser does as part of the pre-flight. So importantly, the pre-flight request is an options request. You can see that options request in the top left-hand side. Now, I mentioned in a previous lesson that without CORS, we can't normally send requests like options, delete, and so on. We can't send requests that are not safe methods. In this case, however, we can actually send as a side effect an options request. So the CORS pre-flight, you can always get to initiate an options request. This usually is not that interesting, but it may be something that if you have a very weirdly behaving application and you need to send a specific options request to it, maybe that would be helpful. I don't think so, but often it's said that you can't ordinarily just send arbitrary options requests, but you can if you use it as a side effect of CORS pre-flight. So side note for security testing. So in the request, we see an additional couple of HTTP request headers, which we're going to talk about later as well. One is requesting the method we'd like to run, and the other is requesting the content type header that we would like to customize for our purpose, indicating that we are sending JSON content. And again, we have the origin specified as https://www.google.com. Of course, the protocol is included in the origin. That's important to keep in mind. Now, in the response, we get a whole number of access control allow headers. We have credentials set to true. We have allow headers indicating that our content type is allowed. We can insert custom data into that content type header. It's also telling us what HTTP methods are allowed, and that includes post, which we made a request for. And finally, it's telling us that the origin that we're sending the request from is allowed. And so the browser takes all of these headers, it validates them against your request, and it will determine whether it should proceed and send the subsequent request, which in this case, because everything we're trying to do is permitted by the server, it is allowed, so that request will go through. So let's touch on some key client-side concepts. Some of these are going to be repeating some items from the last cross-app security session. First, simple versus non-simple requests. Simple requests can be sent without a pre-flight, but non-simple requests require a pre-flight. The pre-flight request, as we discussed, is an HTTP options method request used to determine what the permissions are as far as CORS. So the set of access control allow. There are actually other permission-based headers that a server can return, and we'll look at those later. The mode of a request can be CORS or no CORS with respect to CORS as a mechanism. And this is often implicit, but you can also implicit or explicitly set the CORS mode of requests, declaring whether the client has an intent to actually read the data that is returned. So this is a request property that you can set with fetch. I think one of the screenshots of code I showed earlier illustrated that. And if CORS is not utilized, the response is recognized as opaque. So an opaque response is one where you're not permitted to read, right? So this is a cross-origin request where you haven't been blessed with the permissions of CORS to read that data. And as a result, the response data for that is like empty, like the body is empty if you try to read it. The status is 0. The response type is set to opaque. The browser is trying to really enforce that isolation so you can't infer any data from that response that might let you learn something sensitive that you shouldn't be able to. A quick reminder as to what constitutes simple requests. Generally, permitted HTTP request methods are referred to as get, post, and head for as far as safe methods. Options, again, as a side effect of being able to send a pre-flight. Also, some headers are permitted. There are some exceptions generally to this, but in general, these are simple requests. And looking at setting CORS mode versus no CORS. So this is what using the fetch API with the mode property looks like. In the top example, we're setting it to CORS. In the bottom example, we're setting it to no CORS. And the table here just indicates the behavior of certain headers. So the origin header for CORS requests will always be included. For no CORS requests, if it's a GET request, it's typically omitted. I think cross-origin forms probably include it, if I remember, cross-origin form posts probably include it, if I remember correctly. The secfetch mode header will indicate whether the request is CORS or no CORS. And the secfetch site, assuming we're sending this cross-origin, will always be cross-site. Remember that cross-site implies cross-origin. Little note down at the bottom, the origin header should always be sent for cross-origin HTTP post request due to its historical use in protecting against CSRF attacks. So post generally not safe as far as writes and state changing. So a lot of applications traditionally before modern CSRF protection mechanisms were implemented would validate the origin header against their application. Not the best way to do things for a number of reasons, but it remains, we see things like that where there are necessary features that need to still be implemented for old school protection mechanisms that developers had to implement because of the lack of secure web by default. So one thing that's very much worth examining is CORS in the context of embedded HTML resources. So we're talking about tags like image tags that make requests potentially cross-origin to embed resources. And by default, these are essentially no CORS. So think about images. When you're embedding an image onto your site, you're not trying to read the content with your JavaScript code of that image. You're not trying to see what all the pixel values are. You're embedding that within the page so that the user who's using your application can see the image. So the user can see the image, but your JavaScript can't actually read that image because that would violate the same origin policy. The form tag, as far as I know, is the only HTML element that can send post requests. Otherwise, if you want to send post requests, you've got the fetch API, of course, which can send all kinds of requests. Elements embedding resources from another app are denoted as tainted and cannot be read. So I think Canvas is one important example here where, if I remember correctly, there are different ways in which you can compose Canvas from multiple resources. And of course, any cross-origin resource is going to put that into a tainted state. So you can no longer read that because you'd be violating same origin policy. Now, HTML elements, similar to fetch, but a little bit different, can opt into CORS using the cross-origin attribute. And there are two values for this. One is anonymous. So CORS is used and credentials are only included when same origin. The other option is use credentials, and in this case, CORS is used with credentials. There are a few exceptions to this. One that seems to be prominent is the @font face within CSS, which requires CORS in all cases. A couple other exceptions. The web is always quirky. There are always weird exceptions to standard rules. So I thought that was worth noting, though. From my experience, it doesn't come up often in security testing. Another one that does come up in security testing that is worth pointing out, it's a separate topic from this session, but it's worth being aware of, and that is sub-resource integrity. So sub-resource integrity is a mechanism where you, as a developer of an application, you're embedding resources like JavaScript from a CDN or some other application, and you don't want those to change. You want to verify their values. You want to verify the integrity, right? You have a specific script you want to use. You want to protect yourself against supply chain attacks where an attacker can compromise that script and change its content. So you set the integrity, which is basically taking a hash and saying on your application, grab this script and execute the code, but only if the script matches the hash. But in order to be able to calculate what that hash value is, that's a situation where the browser needs to be able to read the content of that script. And therefore, in order to properly implement sub-resource integrity, those resources need to support CORS for your app to be able to read the raw bytes to calculate the hash. That's something that I think a lot of folks overlook with respect to sub-resource integrity, and it does relate to CORS, so there it is. So when talking about credentials, browsers will include credentials for the target domain, including HTTP cookies, certain types of HTTP authentication, and potentially TLS, like mutual certificate-based authentication. Now, naturally, this does not include bearer tokens or any other custom mechanisms. Those types of mechanisms are seemingly increasingly popular on the web, so a lot of modern web applications really are not using mechanisms where credentials can be automatically sent by the browser for CORS requests. And that often is the big difference between whether a certain CORS configuration, whether insecure or not, poses any type of risk for an application. And there are other rules, of course, even if you're using HTTP cookies, that govern whether a cross-origin request is going to include those. Of course, the most important one that's worth keeping in mind is the same origin attribute of cookies, because if that is set strict, that supersedes these other rules, right? If that cookie is not intended to go to other origins, it won't, even with CORS requests that intend to use credentials. And so if there's a insecure CORS configuration, even with an application that is using cookies, that doesn't necessarily mean that that application is vulnerable. There are other elements to keep in mind when assessing the actual exploitability. The code on screen is just an image tag with a source, and the attribute cross-origin specified to use credentials. Now, we can also interact with the credentials property of the fetch API, which looks a little bit different. The first value is omit, which is just not sending credentials with the request. The default value, however, is same origin. So for same origin fetch requests, the credentials will be included. And then the final value, of course, is include, which includes the credentials, again, when they can be included. So if you have cookies that are permissive enough for the request that you're trying to make, they will be included. Let's talk about some of the credentialed request requirements. Credentials are automatically included for same origin requests. We already mentioned that one. Credential inclusion depends on the credential configuration and browser rules. One thing that I didn't mention, so I talked about credential configuration, thinking about, for example, HTTP cookies and the same site attribute. You also have to consider browser rules. So browsers might apply their own rules, in particular thinking about third-party cookies and the different rules and behaviors across different browsers that govern those. That's also going to impact where and when cookies are going to be sent. Setting fetch credentials to include will send them cross-origin, again, when they can be sent. I mentioned there again, cookies set with same site, strict or lax, will not be sent, or generally I will say will not be sent cross-origin. And of course, again, a browser third-party cookie handling as well is worth considering. Simple requests include credentials without a pre-flight, right? So you're making a very simple GET request. Non-simple requests first send a non-credentialed pre-flight. So that initial options pre-flight request will not contain user credentials. It first goes to the server to ask permission for whether it can make such a request. And then if it's not granted, no request will be sent. The target application, so the one that you're sending a request to, must return CORS headers to define permissions if it wants to relax same origin policy for CORS to succeed and to send a credentialed request. But what we haven't really talked about is how permission is actually granted to the client. We've looked at the headers briefly, but now we'll dive into those in greater depth. So ultimately, the server that you're communicating with, that you're sending requests to, that is going to be the gatekeeper as far as CORS settings. Remember, it's the browser that actually enforces that configuration, but it's the server you're communicating with that can determine when to allow and what types of CORS requests. So the two very important headers for that are first, access control allow origin, which can have three values. First, it can specify a single complete origin. Second, it can specify the asterisk, which indicates a wildcard, so any origin is acceptable. And third, it can actually specify null, but this is best not to be used, and we'll talk about that in a moment. Nevertheless, very much worth keeping in mind from a security testing perspective. The next header, access control allow credentials. This will tell the client whether credential requests are actually permitted and its values are true, or you just omit it, right? So if you don't want credential requests, don't return the header. Although I'm sure if there's any value other than true, that header will be rejected. I haven't personally tested that robustly, but I would expect that to be the case. Of course, many people have said that about many mechanisms that have led to security issues due to assumptions. Nevertheless, we're not going to explore that right now. So you'll often see these headers as abbreviated in this way. So access control allow origin, ACAO. I don't know if people pronounce it ACAO, ACAO. There you have it. So here's how it behaves when you're setting a specific origin. Remember, I mentioned you can only set a single origin in that response. So I'm showing the behavior of different configurations that you might see because developers often misimplement things like this that lead to errors, and indicating here as well the behavior that will occur. So in that first example, what happens if you return access control allow origin? Well, that request should fail, right? It shouldn't allow either of those origins because the ACAO header has not been used correctly. The second one, a domain is specified, but there's no protocol. So it's an incomplete origin. And as a result, that case should also fail. Looking in the third row, access control allow origin is specified with an insecure protocol, HTTP, as opposed to HTTPS. Now, two things to keep in mind. One, this is a valid configuration. So it is a situation where reading over an insecure connection, you could potentially obtain sensitive data. Now, importantly, it needs to match your requesting origin, right? So if you're requesting this from an encrypted connection, the origin is different. Remember, origin takes into consideration protocol. So very likely, if you see that configuration, if the site is only configured to use secure connections, it's probably not exploitable, I'd have to guess. Row number 4, comma-separated origins. Again, you can only specify a single origin, so this is not a header that accepts comma-separated values. That's a violation. The request will fail. And finally, wildcards embedded within the origin that you specify. This is also not supported by CORS, so this will also fail. And down at the bottom, I've noted a digital boundary group finding that we have for security tests. Access control allow origin header returned insecure origin. So this is the case where it does return HTTP://. It's usually an inconsequential finding, but nevertheless, under very special circumstances, it's something that could be insecure and lead to exploitation. The next configuration for the access control allow origin header is what is known as the wildcard configuration. Again, the asterisk, and this permits reading. This allows now CORS from any origin, but there's a really big caveat to that. I don't think this was always the case. I think it was this was implemented after the initial implementation of CORS, but when the wildcard configuration is present, you cannot use access control allow credentials set to true. Browsers will block this because it's such a dangerous configuration. They recognize how dangerous that is. Allowing credentialed requests from anywhere for a lot of applications could be quite risky. So that's not allowed. So what can you do with this? Well, you can make uncredentialed CORS requests, which can still be risky, but it really depends on the application, what it does, how it behaves, what you can do with it. So we do have a finding for that. Wildcard cross-origin resource sharing policy you'll see down at the bottom. And that is worth reporting in situations where there could be abuse from this configuration. One thing that can be a little bit confusing, and I picked this specific example because of that, is that it seems like there might be some like framework and other configurations where a wildcard configuration is considered equivalent to reflecting the origin. I actually couldn't figure that out, but in this case, we see this is a CVE that has resulted from a permissive CORS configuration where we have this allow underscore origins set to a wildcard. It's not clear if that means that that's the wildcard configuration or if that's some framework-specific configuration that allows any origin by reflecting it. I have to assume the latter because the CVSS assigned to this is 9.4, so I assume it was actually exploited, but then again, CVSS scores, CVEs are not always reliable, and we know that this wasn't an old vulnerability prior to the blocking of that insecure combination of the wildcard plus access control allow credentials set to true, because this is a 2025 CVE, so it's relatively recent. Yeah, it's not sure whether it's not clear to me whether this is just maybe not completely or I would say sufficiently communicated, or maybe it was even misreported and misassigned a score. Not clear, but there it is as an example. So I also mentioned a possible value for access control allow origin. That value is null. If you're a developer, do not do this. Maybe there are very weird situations in which it applies, but it's probably a bad idea. Every guide you'll read recommends against it. There are certain origins that may be recognized as falling under null. So redirections across origins, requests from local files, sandbox iframes, requests from data URLs. And here at DBG, again, we have a finding for that. Access control allow origin header set to null. And in fact, much has been written about this, I think largely because of the interest of James Kettle at Portswigger. Portswigger does in general have pretty good resources for CORS testing and security misconfigurations. And again, yeah, I think that's largely because of some of the early efforts of James Kettle. You can see that this article on the left was published as early as October 2016, which I can't remember the date of the inception of CORS, but it was probably relatively recent at that point. So now let's consider the value of the ACAC header in conjunction with the value of the access control allow credentials, or ACAC header, on the very far left. So the first three rows, ACAC is not set, so we're not permitting credentials. The first row, null for ACAC. Again, don't do this. Second row, wildcard. So in this case, the browser can send uncredentialed requests from any origin. The third one, where there's an exact origin, the requesting origin must match the one specified in the ACAC header. And again, the client is restricted to making unauthenticated or uncredentialed requests. The next three rows are the situation where the application is returning an access control allow credentials header and going through the same ACAC values. Again, null, don't do this. Second one, wildcard. This is the forbidden configuration. The browser will block the response. And finally, we have an exact origin that matches the requesting origin. This is the one situation, the combination of you have an exact origin match in the ACAC header and you have ACAC set to true, that the browser can send cross-origin credentialed CORS requests. And then, of course, the consequence of that is that it can read the response. So here's what that looks like if we were making a request from www.example-client.com. We have our access control allow origin, which has an exact origin match, and we have our access control allow credentials set to true. That's worst case scenario that we're looking for from a security perspective in the application response. And of course, this is most dangerous when anything is reflected. So in order to support a large number of potential origins, you don't have to just reflect the value. The proper approach is to allow list. So you know what origins, or you should know what origins are intended to be able to read data from credentialed requests. So the ideal solution is you create that allow list and you have a very strict check against that allow list before returning any one of those values within the access control allow origin header. But this configuration we see on screen here, which is much more permissive, is very, very common, where any value we send within the origin header, the application says, okay, great, here it is, you're permitted. This we call the reflected origin, and it's common because I think a lot of frameworks used to default to this. This is probably less so the case now, and probably more likely the reason this occurs is either because of a misconfiguration by a developer thinking that this configuration did something else, or they're just trying to implement a really permissive policy because they can't figure out CORS and they're trying to get their application to work where they have a client that is making cross-origin requests. So they're like, well, this will work. And especially in development environments where they might be dealing with multiple changing origins over time, this configuration makes it really easy for testing and development. So I think those are ultimately the reasons why this specific configuration is quite common. But again, this is the riskiest possible situation. In the worst case scenario, you can also send credentials like cookies cross-origin, and you can actually read data that is potentially sensitive. So naturally, we have a finding for this at DBG, permissive cross-origin resource sharing policy. There are other issues that can occur when we start to think about other systems working in conjunction with our applications and CORS. And in particular, I'm talking about web caches. So applications that support multiple client origins are very likely to implement a dynamic ACAC header that uses an allow list, like a validated origin. That's the best practice anyways when you need to support multiple origins. And as a result, client or server-side caches may be poisoned if they do not recognize that a changing origin header in the request changes the response content, because the response is going to change those headers, like the CORS headers, to determine whether the requesting origin should actually be able to read that response. And this can result seemingly primarily in two major issues. One is denial of service potential, and the second is potentially cross-site scripting. I won't share the various examples on those. They take a little bit longer to dive into. Actually, I do think I have one example. Yeah, I do. So we'll get to one example in a moment, but there are a few cases of this online. I haven't found a large number of cases of this, but it's worth keeping in mind nevertheless. So the mitigation to this is that caches should, or rather I should say must, recognize origin as a cache key. The cache should recognize that if the origin varies, they should not serve a response that corresponds to a different origin. The response is tied to that origin, and one way that you can enforce this from the server is by specifying the HTTP response header vary origin, which indicates that responses vary based on the origin. And again, we do have a finding at DBG for this. It is insufficient HTTP header cache key specification, which maybe is one of those that's a little bit harder to find. So FYI for our new folks. Here is one of those examples. This one was a denial of service situation, and I think it was quite simple. A request was sent with an origin that was not permitted for CORS, or otherwise would not be the origin that other users would request from, and the server cached that result. And as a result, when users were trying to initiate their own CORS requests, I mean, they wouldn't be necessarily knowingly doing this. Their clients, right? Their browser would be initiating cross-origin CORS requests. If they were served with a response with the poisoned access control allow origin header, or the poisoned response that did not include it. Actually, we do see here at the very bottom of the screenshot, access control allow origin does specify the foo.bar, so the poisoned origin. If you're on a different origin that should be permitted and you get that response, your CORS request is going to be blocked because it doesn't match the origin. So it's a caching situation of the CORS configuration that ultimately results in denial of service condition that is enforced by the browser. So it's kind of an interesting coordination between a client and a server to prevent users from using their applications correctly. So let's talk about some of the CORS-related access control headers that belong in the request that we haven't talked about. So in addition to the actual CORS headers that servers respond with to indicate what permissions they're bestowing on the client, we can, as a client, also include certain HTTP request headers in order to request certain configurations. And importantly, depending on what you send here, you might see very different responses from the server. So this is one of those things that's very important to keep in mind from a security testing perspective. And in my opinion, particularly around, all of these really, all of these headers, I think, are underutilized from a security testing and probing point of view in enumerating what types of requests a remote application is going to let us send from a cross-origin perspective. So the two important headers here, access control request method and access control request headers, are quite simple. They're HTTP request headers that are included when we request to send other methods and other headers that would not normally be permitted. And this can include completely custom values that the server can respond with. And I've seen many applications that will respond similar to insecure configurations of the ACAC header. They'll respond with any method or header that you specify, just reflecting what you send it. So this gives you the capability to send really interesting requests. And if I had to think of a very classic scenario for this, it would be a situation where you have, let's say, cross-site scripting, like a vulnerability in a custom HTTP header, for example, right? And you can't normally coerce a browser to send a cross-origin request with whatever value you want as an attacker within a custom HTTP header, but you can use CORS if it permits it in order to do this. So you could set up a request that would be permitted by CORS, and then you just need to get a user to navigate to your malicious site where you make that CORS request that includes your payload within the header that's permitted by CORS. Another header that does exist and is used by some browsers that I'm not going to talk about now is access control request private network. So don't worry about that, just including it for the sake of completeness here. And in addition to those further request headers, there are also more response headers that I haven't covered yet that are very much worth covering. So access control allow method and access control allow header. These are just the corresponding headers to the request headers. So when you request methods or headers, this is what the server should respond with, allowing the methods or the headers that you submit. And importantly, both for these responses, and I didn't mention it, but for these requests as well, these can be comma separated values, so you can actually request multiple at a time, and the server can respond with multiple at a time. We also have another interesting one, which doesn't come up from my experience a whole lot, but you have access control expose headers, which is a very interesting response header. And what this permits you to do is actually read the value of certain headers, which normally you wouldn't be permitted to do. And I bet there are probably some interesting findings that are waiting to be found by abuse of this header. None of them immediately come to mind from my memory. And then again, we have access control allow private network, which again, I will discuss this in a later session. And finally, we have access control max age, which relates specifically to caching, which we'll talk about in the next slide. Before that, just as a refresher, or maybe if it's new to you, there are many HTTP headers that can have multiple values. These are known as list valued headers. So in this case, if you look at the screenshots, I have two examples that are equivalent. Access control allow methods supports multiple values, so you can either have them comma separated, or you can have them independently appear on separate lines specifying the name of that header in each situation. Now, as I mentioned, there's one more header, access control max age, which we didn't define. Well, now we're doing that. This relates to pre-flight caching, which is where browsers cache permissions returned from an initial pre-flight. So what the header does is it tells the browser how long to cache permissions, right? Situation is you make a CORS request, there's an options request that enumerates permissions that you have, and then the browser will remember those permissions. So in subsequent requests within that timeline, it will not send another options request. And this is largely a mechanism, as with any mechanism, to avoid sending unnecessary traffic. So improves the speed of client-side applications, reduces the load of browsers, that sort of thing. It might be relevant in very rare security-related situations. I've at least had one scenario where we had to dive into how this mechanism worked. I think in general, it's rarely likely to be a concern, but it's nevertheless worth knowing about. Now, just as in the last session, there are elements of cross-origin resource sharing that very much apply to cross-site request forgery and related attacks, and we will not have time to cover that in this session. So that will, again, be in a dedicated CSRF session. It is worthwhile now to talk about the OWASP Application Security Verification Standard and the requirements that it dictates for applications and their implementation of CORS. So I'm going to discuss those now. These appear all in the same chapter, but across two different sections: 3.4 browser security mechanism headers and 3.5 browser origin separation. So the first one, 3.4.2, verify that access control allow origin is fixed or allow listed. So don't use reflected values. Obviously, if you see reflected values, that is a great hint that there might be something to abuse as a security tester. Ideally, it should be fixed to one value or drawn from an allow list of known origins that should be able to make permissive CORS requests. Then we have 3.5.1, do not rely on CORS pre-flight to block requests. So even though you can use CORS to open up the types of requests that you can send from the client side, it shouldn't be relied on a mechanism to block requests. And remember, the only thing it really lets us do is make clients send requests that we couldn't normally send. If we're in burp and manipulating traffic, we can still send any request that we want. CORS is just something that enables us to send more requests from, let's say, a malicious site that we make in JavaScript. 3.5.2, if CORS preflight is relied on to prevent origin use of sensitive, I think that I meant to type out cross-origin use of sensitive functionality, ensure that the functionality does require preflight. So what that in part comes down to is making sure that the functionality where you expect CORS to actually be used, like you're expecting some level of cross-origin integration and reads, it's a very good idea to make it so that that functionality works in a way that requires the CORS preflight. So, for example, don't use simple HTTP methods. Use something that will require that preflight request to add that additional protection of that preflight process. And finally, security testing considerations. The first thing I have to say about this is ask and you might receive. Now, there are increasingly scanners that do a large number of checks for cross-origin resource sharing. In my opinion, they're not sufficient. There are a lot of things that are not being checked. There are a lot of deficiencies. They're not necessarily doing a lot of work in testing the validation of origins. I'll talk about that in a moment. But beyond just the origin header, also think about the access control request headers. Try sending those, including different values. See what the remote server will let you do as far as CORS functionality. Insecure configurations, of course, are definitely a great start when investigating how to abuse CORS. If you have credentials being allowed and a reflected origin, the next step to look at is, does this apply to that application? Can it be abused? Is it using overly permissive cookies? Is it using some other way to manage credentials or sessions that can be abused by using that permissive CORS policy? When I mentioned, scanners might be incomplete in certain tests, evaluate fully any server-side origin allow list. So many applications do not implement a fixed value or an allow list. Some will accept subdomains. Some will do a simple string match, right? So all they need to see is that specific ETLD plus 1. If they see that anywhere in an origin header, they'll accept the request. And so you can make all kinds of origins that use that. You could even use that as a subdomain, right? Google.com.your domain that you control. So that would be the abuse of a simple string match. And also regular expressions are definitely used by a certain number of frameworks as far as validating the origin header. And for sure, there are probably ways that these can be abused across a number of applications. So it's worth not just trying a malicious origin, but thinking about the ways in which you might construct a malicious origin that are bypassing whatever validation logic the application is using to dynamically construct an origin to include in the access control allow origin header. And finally, and this really applies to every security mechanism, there are probably always going to be application level and framework level implementation quirks. With all of these values, how are they handling special characters? How are they handling white space? Casing. I think there have been a few examples where there have been casing issues from CORS implementations. There are probably all kinds of things that I can't even conceive of right now. As with all security testing, we don't really know of the issues we don't know about. But the important thing is that we know the basics, how CORS works, and hopefully this session will help you understand that and help you apply it in practice. And that's it.